I built a system that can save a failing UAV from crashing into the ground by using parachutes. 3, 2, 1, go. A few years ago, I had the idea to build a SpaceX-like rocket using an electric ducted fan. Now, I've seen other YouTubers attempting it, but they primarily focused on hovering the rocket and using it as a singlecopter. I want my design to reach high altitudes, pick up significant amounts of speed, and be able to be in free fall for most of its descent. Other than drones, singlecopters only have one propeller and use control surfaces to change the direction of thrust. At that exact moment, I realized I was running into a bit of a problem here. We're talking about EDFs that cost around $300, controllers $300, batteries $200, transmitters $200, servos $100, and the construction itself at least $100, but 100 hours of construction time. There is no way I will send this expensive technology high up into the air without a separate safety system that always lands the rocket gently. Now what do we need? First, a redundant parachute deployment system. Second, an independent controller with its own power source. Third, simple but reliable software. And fourth, testing, testing, and testing. Let's begin. I started by ordering 2 parachutes and professionally tested how much space they needed when fully compressed. I then engineered a cylindrical compartment with a spring-loaded piston that is held down by a small pin. And this is what it looks like after 3D printing the parts. Spring, piston. Here you can see the pin that holds down the piston. And if you release the pin, which should be enough to eject the parachute, but when eject the parachute, we need to know the system's altitude to determine the release point. But how on earth will the system know its height above the ground? We'll be using this device. This is a barometric pressure sensor, and as air pressure falls the higher you get, we can use it to measure the system's altitude. But how on earth will a pressure measurement become an altitude measurement? Let me explain using Jenga blocks. If you want to find out what pressure this Jenga block puts on the table, it's very easy. Pressure is just defined as force divided by area, so the gravitational force of this Jenga block divided by the area that touches the table. And by the way, we can find out its gravitational force by multiplying its density with its volume and the gravitational constant g. Now if I add 2 other blocks, the pressure on the table is higher than the pressure on the first block, which is higher than the pressure on the second block, and so on and so on. And as air isn't made up of blocks, the trick is to think about air as an infinite number of infinitely small blocks. Now back to the equations. You can see that the block's area and volume share 2 factors, a and b. That allows us to cancel them out of the equation. Now we rename the other dimension to h for height. The positive direction for h points up, the weight force points down. That means the equation has to be negative to get the directions right. The air density is also not constant, so we rearrange the general gas equation and replace it. Dealing with infinitely small block heights is an application of calculus. This d in front of p and h signals that an infinitely small change in height will result in an infinitely small change in pressure. And now we can solve this equation for h by integrating. Now for those of you wondering how accurate this is, I can measure differences in height smaller than 1 meter. Now for those of you wondering how accurate this is, I can track the pressure sensor with my camera because I built a contraption that tilts it according to the calculation of the sensor's height. I think that's insane. Okay, now we know when to deploy the parachute, but how will the system actually release it? We'll be using a technology I call BRIPTURG, which stands for Brass Rods I Bent to Interconnect Ridiculous Geometries. And I use it a lot. You can see that the pin is spring-loaded and is connected to this lever. Now the grip Turk locks the lever in place, but if it is drawn back by this servo, it releases. And now it is time to involve my health and safety official to see what she thinks. After the demonstration, I applied for an operating license, but she refused to issue one. So, yeah. Let's talk about software, because finding the sweet spot for parachute deployment is harder than you might think. If the parachute deploys too late, the system will be way too fast and crash. But if it deploys too early, the parachute will be a significant area of attack for wind, which could make my system drift away. Parachute physics is actually quite complex and is empirically tested for large parachutes with known Reynolds numbers. I have a small parachute with an unknown Reynolds number, so any scientific calculation is out of place here. I found some information about inflation times, etc., but I decided to kick the choice of the deployment logic to the testing phase and for now just prepare the rest of the software. First, connect an RC receiver to an Arduino Nano and write software that tracks the signal from my remote control. This allows for manual commands to the system while it's in the air. Second, connect the pressure sensor and the servo to the Arduino. Now write software that triggers the deployment on manual command or on a pressure event. Third, connect a super small LiPo battery to the Arduino, which powers every subsystem and satisfies the requirement of an independent controller with its own power source. Speaking of requirements, let's have a look. We'll find out about the system's performance and software reliability in the testing phase. We have an independent controller, but what exactly makes the parachute deployment redundant? And this is where the Drogue chute comes in. Drogue chutes are often used in aerospace to slow down falling objects, to gain stability, or as a pilot chute to deploy a larger parachute. For us, this means there has to be another deployment mechanism that releases the Drogue chute first, which then pulls out the main chute. At first, I wanted to go with some kind of a fairing with a special compartment for the Drogue chute. And when the fairing opens, the chute comes out. But then I scrapped the idea because I don't have the rocket yet and we will test the system with a drone. Therefore it has to be as light as possible, and so I went with a smaller Drogue deployment system. Basically, it's a door that swings open and the chute falls out. Now, how does the transition from the Drogue to the main chute work? First, I installed a lid on top of the main chute compartment that is held down by small magnets. This helps to keep the chute inside when it's compressed. And second, there is another lever that is locked in place by a grip Turk, which holds the drag force of the Drogue chute until... And after the lever rotates, the Drogue chute is free and serves as a secondary release mechanism. That's it! The system is complete and we're ready for the first tests of the transition between the Drogue and the main chute. Now on to some real testing. As I mentioned before, we'll test the system with a drone. This allows us to deploy the Drogue chute while the drone remains in stable flight, and the drone could take over again should the system not work correctly. First, we lift the system up in the air. Then we deploy the Drogue chute and command the drone to sink as fast as possible. Now back to the deployment logic. I found that the system reaches terminal velocity quickly during the descent, even under the smaller Drogue chute. So if a fail is detected, it makes sense to deploy the Drogue chute instantly because this stabilizes and slows down the descent. And when it reaches a given height, the main chute deploys.
And it makes sense for us to hard code this height because the descent velocity will more or less be the same every time, and I roughly know when to expect main chute deployment, so I could intervene manually if something goes wrong. And that's what we tested again. Thank you very much for watching and see you soon.